I'm like, wait, what is chemical potential? Then my wife and I have huge arguments because she also does thermodynamics, and then, well, we stopped talking thermodynamics in our home because it was Pakoda had to come and like interfere. So let's write down G. What is the natural variable? What is the natural variable for G? Anyone remembers? P, T, and N, right? So we can write down dG is equal to V dP minus S dt plus mu dN, right? It's very similar to the relation Lydia wrote over here. So this plus mu dN shows up in everything, right? Anytime you have to write down a fundamental relation, you know there's always going to be N, and you know always going to be plus mu, right? It's really, how do you get mu? What do you keep constant? That is the thing that changes. And a better way of thinking about it, especially as we go further, is to think about not just one chemical in the system, but more than one chemical. So we have mu1 d1, we have mu2 dn2, plus we have mu3 dn3, dot dot dot. Okay. So in this case, we can define mu1 as partial G by partial N1, keeping pressure, temperature, and 2 and 3, all these things constant, right? This is not all that different from what we did over here. This is the same definition. And I'm so happy that you brought this up, because we are going to use the chemical potential even more in constructing phase diagrams. So, and if you are on shaky grounds here, that will be like even shakier. Okay. So with G, we had a special relation for mu, right? And that relation is what you showed in problem 6a. G is equal to summation mu I ni, right? It's not true for A. A is not equal to mu I ni, right? So we also have G is equal to summation I is equal to 1 to K mu I ni, right? This is a very special relation, okay, that exists only between G and mu. We don't have such a relation between A and mu. We don't have such a relation between S and mu, only G and mu. This, so in other words, one way, so let's think about chemical potential. So one way of thinking about chemical potential is component 1 will move from high mu1 to low mu1, right? If you have high chemical potential somewhere, it will move from there to low chemical potential until the chemical potential becomes equal. Chemical potential equal does not mean that component 1 is not moving. What it means is that on an average, it is moving the same, right? It is moving the same from A to B. So on an average, there is no flux now. It balances out, right? Another way of thinking about chemical potential is through this relation, G is equal to I is equal to 1 to K mu I ni. And this becomes even more useful if you have a one-component system. If you have a one-component system, then what is G in terms of mu and n? It is mu multiplied by n, right? So for one component system. So a one component system, chemical potential is the same as molar Gibbs free energy. Okay? Yeah.
So when we like created that relation, right, we got that by writing the fundamental equation for G and then assuming like a constant temperature. Sorry, constant temperature and like pressure process.
But it's a state function, so the process goes away. That's the beauty of state functions.
Okay, so then like for example, if I have like dg, dp, or something like that, can I just pop un in there for G and then like continue taking derivatives and stuff like that? Like,
are you still talking about your homework problem? Is that bothering you?
Okay. I'm talking about more general class problems.
Yeah, you can if you're careful. Yes, you can. You can. The reason the proof that Anjali is talking about, when we got to this relation, we talked about the constant temperature and pressure process, right? And then we got this relation. We said now it's going to be true for always, because now there is no change here. This is the value of a state. This is a state function, so it does not matter what process you use to derive it.
So if I integrate a state function,
the process just doesn't matter.
Okay.
That's the beauty. That's why state functions are so special.
It doesn't matter like what process you're doing. If you take the integral of the derivative,
yeah. Unlike Q, it will matter for Q, right? Unlike W and Q, you have to be very careful for what is the path, right? For S, for G, for H, for A, doesn't matter. That's why they're so special. So, any more questions? So, yeah, go ahead.
So this mu,
Uh-huh.
if we are using the definition of partial E partial N,
Mhm.
that mu will have, it would be a function that could possibly depend on N.
Exactly. So
But-
this mu is always a function of n. The thing is, what else is it is a function of? If you are writing mu this way, then mu is a function of n, s, and v.
Right, but in the case of G, it will not be a function of N.
It will still be a function of n. Inside,
But
in
it-
addition to it, it will be a function of p and t. And on n, it is linear, which is the funny thing, which is
But
crazy.
Here it won't be linear.
It won't be linear, no. This linearity only shows up for G. So yeah, and for one component system, it is just the Moser-Gibbs free energy. For a multi-component system, you still have to take the slope, right? You still have to differentiate, but it's an easy differential. Does that make things any better, Lydia? Or... No? Oh no, I'm going to hide it here.
Mathematically, I'm fine. Like I get all the. I'm just like.
Okay, it will.
physically,
We will
where's the
use. We will
change in
use. Okay, so
Like, is that
physically,
bond energy? Like what is happening?
everything is bond energy, right? Because where does G come from? G comes from H minus
Does
Ts.
like a one atom system not have chemical potential?
Does a one atom system have Gibbs free energy? First of all, you have to remember thermodynamics does not apply to one atom, right? Thermodynamics applies to not one Lydia, but a lot of Lydias. Let's imagine
Well,
an
a lot.
Avogadro number of Lydias,
Right.
okay?
But there's no Lydia bonds, so.
You can still write down the chemical potential.
But where-
Think about if
where-
Lydia was an ideal gas, we did that, right? She remembers that equation, right? The Sackur-Tetrode equation. We did that for an ideal gas. It did have an entropy, and it's dependent on the volume. So if there was no Lydia bonds, the entropy would depend logarithmically on the volume, right? So where does Gibbs free energy come from? Gibbs free energy comes from H minus Ts, right? H is U plus PV minus Ts. For a system made of Lydias with no Lydia bonds, this is going to be, let's assume Lydia is an ideal gas, point like 3/2 nRT plus nRT minus Ts, right? And Ts, what is S? It is some proportionality constant, let's call it K0 multiplied by log of volume. So this is the Gibbs free energy. Okay, and if I want, and let's keep the extensive property over here. So if I want the chemical potential of a bunch of Lydias where there is no Lydia bond, it's going to be this divided by n. That's the chemical potential. Does it give you intuition? No, this is the math that I wrote down. Okay, intuition will, the best way to get intuition for chemical potential is to remember this point number one, that it moves from high chemical potential to low chemical potential. And that is really, since it's so connected to G, it's not just about the bond energy, okay? Why did a system made up of particles which don't have bonds still have chemical potential? Because of entropy, right? If you went to zero temperature, then that becomes simpler. If you go to high temperature, entropy plays a role. So chemical potential, yeah, 1 minute, then accounts for energy as well as entropy. Okay, go ahead, Ben.
So it's easy to kind of imagine how you measure pressure in a system. Can you apply that to chemical? Like, how do you measure chemical potential?
Oh, remember fugacity? That's what was, why did we talk about fugacity? There was an equation we liked so much that we wanted to write an equation like that for everything else. That is how it came, right? We wrote down this equation, mu is equal to mu naught plus RT ln P. That is how you measure chemical potential. But this is true only for an ideal gas, right?
Okay, well, still, that's much more complicated than just like a barometer. Something to measure pressure.
Really? All you need to do is to use a barometer, take a log, multiply by RT.
That's like a. That's
Why is that
directly
complicated?
You're not directly measuring chemical potential.
No, you're measuring pressure and then you get chemical potential. Why is this? Don't tell me this equation is very complicated. We have done way more complicated equation. If you know the pressure, take the log of pressure, multiply by RT. This is just a constant. We don't care about it, right? Because we are interested in changing chemical potential. So it's quite easy. Unfortunately, this is only true for an ideal gas, right? For a real gas, we use fugacity. That makes things complicated. And then for fugacity, then we have to measure excess volume and things like that, right? So there is a way around. Any more questions? So in thermodynamics, the two most complicated concepts are, number one is fugacity, number two is chemical potential. Fugacity, and actually there is a third one which is called activity. the reason activity and fugacity are complicated because they talk about non-ideal behavior. Chemical potential is complicated even though if you assume ideal behavior is still complicated, like where did this come from, right? The chemical potential of an ideal gas, it looks so bizarre, but it captures that it's not just bond energies, it's also entropy, the number of ways of arranging things, right? So yeah, any more questions? So we are going to use chemical potential in what comes next. And you will, that's why I also do phase diagrams, because if you don't cover phase diagrams, then you never really understand chemical potential. Phase diagrams, and especially what is known as this common tangent rule, will give you a sense for how chemical potential works in practice, what are its implications, okay? Good, so let's resume what we were talking about last time. So last time we were talking about solutions, right? We talked about ideal solutions, and we talked about regular solutions. For ideal solutions, the enthalpy of mixing was 0, right? And the entropy of mixing, does anyone remember the expression for a 2-component ideal solution? Oh, it's the most beautiful expression in thermodynamics. Is minus R XA ln XA plus XB ln XB, right? It's the same formula that Shannon has in his information theory. For regular solution, what do we do with delta mixing of H? Anyone remembers? Go ahead. XA, XB, and what was the name of the proportionality constant? Omega. Doesn't matter, we can call it Anjali. No, it doesn't matter, it's a proportionality constant. And what about delta mixing S for a regular solution? We kept it the same as the ideal. Why did we do that? Because, well, we can do it what we want. This is how we are defining the solution. This is how we are defining the model. Turns out this is also quite useful. Accounting for better entropy models is really, really hard. I want to make a point here. So the model that we are studying now, so what we are going to do next is to derive an expression for omega. And omega will turn out to be Z, the coordination number. So how many neighbors does A and B have? I will make my point just in a bit. So omega will turn out to be Z, which is the coordination number. And we assume it is the same for A and B. You can generalize it if you want. Multiplied by the bond depth, the negative number corresponding to how stable the bond is of AB, minus epsilon AA plus epsilon BB divided by 2. So this model, this expression for omega, so you can have a regular solution model where you just keep omega as a fitting constant, okay? You don't care about where it comes from. But this particular expression that I wrote for omega is known as the quasi-chemical model. It's also known as the Bragg-Williams approximation. Does anyone know the name of Bragg? Bragg peak. X-ray, right? What else is special about Bragg? It's the same Bragg.
I just know that.
So he won the Nobel Prize for X-ray for that work.
The one that he shared with his father.
With his father. He was 24 and his father was like 40, and they both got the Nobel Prizes together. I don't think that has happened ever again for a father-son pair. It happened in economics 3 years ago, a husband-wife pair, and I think a husband-wife pair is more common, but a father-son pair. And he still continues to be the youngest Nobel laureate. So it's too late for any of us. He won it at 24, which is kind of crazy. I mean, now the Nobel Prize has also become a bit political. We have to spend a lot of time. Yeah, that's another discussion. So what we are going to show is this omega, okay? And then I will recap some of the things we talked about last time. Last time we also plotted delta S mix versus X, right? And that was always negative. The entropy contribution always favored mixing. And we looked at 2 values of omega, positive or negative. And we saw that there was a difference between high temperature and low temperature, okay? So, but let's talk about this omega. Where does omega come out to be this one? And in total, then our delta mixing G is omega XA XB plus RT XA ln XA plus XB ln XB. So let's try to understand this omega. Or the quasi-chemical model. And in thermodynamics, we are really not talking about bonds and atoms. We know it comes from you, but we are doing classical thermodynamics. It existed before people even agreed upon the existence of atoms. So it's robust. But I like this proof because it shows us, it gives us something very concrete about omega sinus. It's really nice. So in order to do this, we are going to make two assumptions. First assumption will be that delta mixing H is the same as delta mixing U. When would you expect such an assumption to be valid? Go ahead, sir.
Constant volume.
Let's say volume is changing. You're in the right direction. When do you expect volume change to be more or less constant? Yes, there it's definitely constant, but in non-closed system, if there are no gases involved, right? Or if the same number of gases are involved, volume change really happens when a solid changes into gases. If you have a chemical reaction where everything, let's say this iPad, this battery in my phone is undergoing some solid state reaction. Does the phone suddenly become like boom, transformer size 50 times bigger, right? It's not going to happen. But if something blew off in this, then yeah, sure, the volume could become much bigger, right? So what we mean here is H is equal to U plus PV. So like Stephen said, we are ignoring change in PV, which is okay if, that is okay if no gases involved at all, or same moles of gases. So you don't, even if you have gases playing a role in the reaction, let's say they are not changing drastically, right? If you have something like H2 plus O2 combining to form water, then of course this is not a good idea, right? Then you have to be very, very careful. Okay, so that's our limit here. The second assumption is we always have a random arrangement of atoms. This is kind of philosophical, but you will see why it makes sense, okay? So we always have a random arrangement of atoms. And let's say we have PAA number of what can I say? Okay, looks like it's back. Okay, it's recording and screen share is, I think screen share is working. We'll find out. Okay, and PAB number of AB pairs. And so we are talking about nearest neighbor pairs. Okay, so we are assuming a solid, we are assuming some sort of crystalline lattice exists, right? So we have something like a lattice where we have A, B, A, B, B, A, B, some sort of arrangement, okay? And we are counting how many. So here we can see there is one AB pair, there is another AB pair, there is one more AB pair, there is one more AB pair, there is one more AB pair. Okay, so we are counting this over the whole system. Okay, we are not counting neighbors which are further out. In this system, what is Z? What is the coordination number? The thing that I drew. Everything has 4 neighbors, right? So you can think about neighbors like this, like this, like this, or this. Here Z is equal to 4. So the number of coordination number you are given, okay? So this is our assumption. So now that we have this written, can you tell me how to write? And if you like math, especially discrete math, then this part should be of interest to you. How do I write PAB as a function of Z, as a function of the total number of atoms, and what else is needed? So let me give you a hint. PAB will depend on Z multiplied by N total. Does this make sense? If the coordination number was 0, would you have any AB bonds? There is no coordination, right? We just reduced it. If you have higher coordination, the number of AB bonds should go up. But this is not complete. Something is missing here. If you had 0A in the system, what would be the number of AB bonds? If you had 0B in the system, what would be the number of AB bonds? 0. So it should depend on the mole fraction of A and B, right? Should it depend in a different way on the mole fractions of A and B? It's a random arrangement. A and B are treated equally. Thus, this should be XA multiplied by XB. Okay? So PAB is equal to Z multiplied by total number of atoms multiplied by XA multiplied by XB. Okay? Let me write down this equation on the next page again. So we just showed that PAB is equal to Z multiplied by N total multiplied by XA multiplied by XB. Okay. So we said that delta mixing H is going to be approximated by delta mixing U. So let's calculate delta mixing U explicitly. Let's get it done. So what is delta mixing U? Delta mixing U is U of this solution minus U unmixed. And before you forget what are we talking about in the first place, and it's possible that you have forgotten, let me draw a picture just to remind you. The setup that we are talking about is initially we have a box like this. Finally, we have a box like this. Initially, we had A on the left side and B on the right side. And then we have let everything mix. Okay, that's the setup that we are talking about. We have some chemical 1, chemical 2, and we mix it together. Okay, so this is initial or unmixed. And this is our solution. Okay, let's talk about U unmixed. The potential energy of the unmixed system where you have A atoms on the left and B atoms on the right. And the coordination number is kept the same. Okay. And another picture I would like to draw for you is the picture regarding the bonds. So I said that any given bond, like the AA bond, corresponds to a bond strength of epsilon AA. Okay. So what is the total potential energy of A atoms? Ignore B completely. What is the potential energy of one pair of A atoms? Again, let's go to our Lydia bond example. Now Lydia is actually has a bond with the other Lydias and the bond strength is epsilon AA. So if I have one Lydia bond, its energy is epsilon AA, right? That's it. So it's going to be proportional to epsilon AA. But how many Lydia bonds do I have? And again, even though I drew it as a haphazard arrangement, we are assuming that a crystal exists, right? So it's something like this, okay? It's only A's and your coordination number is Z. So the number of Lydia bonds is going to depend on the coordination number, right? So it should be proportional to Z. Or let's simplify it. So each pair of AA atoms gives you a bond energy of epsilon AA. How many pairs of AA atoms do you have? That's the question. Yes, let me help you a little bit more. Don't use the mole fraction, use Na, the total number of A atoms, which is similar, right? So the reason why I wouldn't use mole fraction is because you have absolutely the right idea, because we are not talking about intensive quantity, right? We are talking about, so yes, correct. So Maria Delia wants to use Na, the total number of A atoms. So it will depend on Na, right? If there was no A atom, it would be 0, right? But what else should it depend on? What is the total number of AA pairs? Z multiplied by Na. But is that correct? So if you think of this picture, how many AA bonds is this A atom forming? Number 1, number 2, number 3, number 4, right? So the coordination number is 4 and you formed 4 bonds. And you can count similarly 4 bonds for every other atom. But you doubled it. So you have to divide by 2. Okay?
So each dot is a
atom.
A atom.
Yeah.
Although you cross over, I mean, 5 in the center, are you counting now?
So this is my A atom, and I'm counting its number of neighbors. It has neighbor number 1, neighbor number 2, neighbor number 3, neighbor number 4. I can't bond with myself. It's kind of strange, you know. So 1, 2, 3, 4. Okay? Yeah, go ahead.
Sorry, I like don't know this. Is the coordination number just like the number of atoms that it?
Number of atoms that are close enough to form a bond.
So.
We could define that would be the second coordination shell. Okay.
Okay.
So we could define third coordination shell. And in reality, yeah, bonding is happening with all atoms at all particular distances, right? We just stop it at a certain level. Okay. So U unmixed will be ZNA by 2 multiplied by epsilon AA. But that's only for A, right? We have to have a similar expression for B also, right? And now that will be super easy. It will be ZNB by 2 multiplied by epsilon BB. Let's call this equation as 2, and let's call the U unmixed equation as 3. Okay, so we got U unmixed. Now we have to talk about U solution. How do I write down U solution? Let me generalize this expression in a similar way. Okay, U solution will be PAA, number of AA bonds, multiplied by epsilon AA, plus PBB, number of BB bonds, multiplied by epsilon BB, plus PAB, number of AB bonds, multiplied by epsilon AB. And remember, we just wrote down PAB on the top of this page, equation number 1. So we already have PAB, but we want to do something with PA and PBB and simplify this expression. So can you change PAA, PBB, and PAB independently? You cannot. Why, Maria?
Doesn't multiply depends also?
Yeah, but if you have a fixed number of A and B atoms, and you can arrange them separately, so the number of AA bonds and BB bond will change. But it will change something else, right? You cannot just increase all the number of bonds, right? Unless you are willing to change the coordination number itself. That's the only way you can do it, right? To make it higher coordination number, right? So we have to write down an equation connecting PAA with PAB, okay? And that equation is the most subtle argument in this argument. That is the one where students get confused. If you understand that, everything else is very easy. So I'm going to turn the page. So the physical argument here is that PAA, PAB, PBB are connected. They cannot be varied independently. What is this connection? We have kind of seen it. The best way to understand it is how we wrote down U unmixed. For U unmixed, this thing in the red bracket, that is PAA, right? That is number of AA bonds that you formed for a system made up of only A's, right? So you can see that ZNA is equal to 2PAA for unmixed A, right? But now we have mixed things. So there has to be a correction. So what are you saying here? You're saying here that you are counting the number of A atoms and multiplying it with the coordination number, right? So what is ZNA? ZNA is the total number of bonds that an A atom can form in the system. If it was a pure system, it would be just 2PA, taking double counting into account, right? That's how we did over here. We wrote down PAA for unmixed to be ZNA by 2. Here, there is a difference. What is that correction coming from? Should it depend on PBB? Should it depend on PAB? What else can an A atom do? An A atom can form a bond with A. An A atom can form a bond with B, right? So it does not make any sense to talk about BB because we have already fixed one A atom, right? This is simply going to be PBB. Sorry, I said the same. PAB. Okay. I'm going to star this one because this is a bit slightly subtle argument. And again, the way to understand it is that this is true for unmixed A, okay? And this is correction due to mixing, okay? So if it confuses you, go and stare at it. It will make sense by understanding the limit. Yeah, go ahead.
So, were we having a correction to it to mixing if we have an
Say again.
were we having a correction of mixing when we're having unmixed equation?
No, but, oh, okay, that's, this is maybe confusing you here. This is, the whole thing is true for solution. What I meant to say is that ZNA is equal to 2PAA for unmixed, okay? In an unmixed solution, because that is what we used in deriving equation 3. We used this in equation 3. In mixture, ZNA is equal to PAB plus 2PAA. And let's call this equation number 5. So now we are ready to write down, we can take equation 5 and put it in equation 4. Equation 4 is the expression for U solution, right? So let's do that. So equation 4 said U solution is equal to PAA multiplied by epsilon AA plus PBB multiplied by epsilon BB plus PAB multiplied by epsilon AB, right? So now what we can do is to keep epsilon AA and replace this PAA with ZNA minus PAB, okay? So this PAA now becomes ZNA minus PAB divided by 2 plus epsilon BB ZNB minus PAB divided by 2, right? Just as identical equation to equation 5 for, yeah, go ahead.
So for this whole situation, we're saying that we have one component of one crystal lattice, whatever,
The same crystal lattice on which you could have A's and you could have B's.
and then we
Mix
remove
them together.
imaginary. When
Yeah,
we
so-
have to put in work to mix them.
So, no. The crystal lattice is things diffuse. That's the process of
I don't know
diffusion.
inorganic.
Oh, even I don't know. I don't have any degrees in
But
this.
I'm thinking like if I put a.
No,
block
don't
of
even
such
think
a
about
mixture
crystal.
of
Don't think
blocks-
about crystal. The coordination number concept applies even to liquid.
Okay,
Okay, you could have two liquids. It becomes simpler if you think about oil and water. Okay, they are not going to mix entirely, but there will be some mixing, right? Or what are, you guys are better chemists than me, and what are two other liquids that you can think of that mix more? Ethanol water, they mix perfectly. Oh yeah, that's what we're going to do next. Ethanol water, right? So if you put ethanol water, ethanol is not sitting on a crystal lattice, right? But if you count, if you go to an atom in ethanol and you count how many neighbors do you have, you will find that it peaks somewhere around 10. Z is approximately 10, even in liquid. In gas, it becomes even more diffuse. You will look at these curves in StatMech next semester. So yeah, that's the physical picture. So plus PAB epsilon AB. Okay, so all I have done is to replace PAA using this equation and and PBB using a similar equation. Okay,
How did you calculate it?
P. No, we don't know how to calculate P. That's what we are doing. We are going to get rid of it. All we know is how to calculate PAB.
Oh, in this case, P is no part of pressure, right?
No. This is a number. It's bad notation. P is nothing to do with pressure. It is related. It is the number of AB pairs you have. Okay, PAB is the number of AB pairs, and we know PAB is equal to Z and total multiplied by XA XB. So what we have done now is to get rid of PAA and PBB and written it completely in terms of PAB. Okay, and we can simplify this expression. Once we simplify this expression, how do we simplify it? We take epsilon AA ZNA, and that becomes NAZ by 2 multiplied by epsilon AA. Then we take epsilon BB ZNB, and that becomes NB Z by 2 epsilon BB. And everything else is proportional to PAB, right? So we can put PAB outside, and that becomes PAB multiplied by epsilon AB minus epsilon AA plus epsilon BB by 2. Almost there. This first part, have we just seen it? We just gave this thing a name. I will turn the page and then you'll see it. What is this thing over here in the blue oval? That is U unmixed. Look at equation 3. U unmixed is ZNA by 2 multiplied by epsilon AA plus ZNB by 2 multiplied by epsilon BB. This is U unmixed, right? This whole thing is U unmixed as per equation 3. Okay, so now we can write down this equation in a simpler form. We have, and I will move to next page.
So the way you calculated the probability of AB,
Mhm.
you assume I have this empty lattice hole and then have probability. there.
It's random arrangement, yes.
So then if I have half and half, then how come I cannot make the assumption for A and B?
We are doing it after mixing. PAB is done after mixing. Okay? PAB is done after mixing. If you think carefully, you will realize that I see where it's come from. It looks like PAB showed up in the expression for U unmixed, right? And how are we talking about U unmixed, PAB and U unmixed? But if you look at the derivation carefully, trust me, you will see that there's no contradiction. Okay. It's not probability, it's the number of atoms. It's the number of atoms. I mean, we could have used, it's the pairs, number of pairs. That's why I'm using P. Okay, let me write down in the very beginning. P, oh, actually I did, right? Look, P pairs, that's where it comes from.
So one pair is one bond.
One pair is what?
One bond.
Yeah, exactly. Don't doubt yourself, exactly correct. Okay, so what do we have? We just showed that U solution. By the way, I will, if someone reminds me, I can post very cleanly written notes of this online, so you can work through the argument very, very carefully and see what's going on, okay, on the Braggs-Williams for like chemical. So everything will come here. Go ahead.
There's something that was bothering me about the coordination number.
Uh-huh.
Can you go back one? Yeah, so like 1, 2, 3, 4. Like, aren't you counting the central atom like multiple times when you're talking about?
That's why we divided by 2. I am talking about the coordination number of any one atom. Let's go to you. What's your coordination number? 1, 2, 3, 4. But I have to focus on you to calculate the coordination number first, right? So I focused on any one atom.
Okay.
That's why I did that. And again, I drew lattice because it makes things simpler. We can talk about coordination number even in liquid. In liquid, the coordination number is not a delta function, it's a Gaussian. It becomes square. That's the idea. And you can measure it through scattering. So U solution is equal to U unmixed, because all of that is U unmixed, plus PAB epsilon AB minus epsilon AA plus epsilon BB by 2. So now we can write down our delta U mixed, delta U mixing, right? So delta mixing of U is equal to U solution minus U unmixed. And what is that? That is PAB epsilon AB minus epsilon AA plus epsilon BB by 2. Let's call this equation number 6. And now let's use our equation number 1, the expression for PAB, which is Z n total multiplied by XA XB. Use equation 1 in equation 6. Then we get delta mixing U is equal to N multiplied by XA multiplied by XB multiplied by coordination number, epsilon AB minus epsilon AA plus epsilon BB by 2. And if we are interested in mixing, delta mixing U per mole, right, then we just divide by N, okay? So therefore, we can now write down the full delta mixing G per mole. That will be delta mixing U per mole minus T delta mixing S per mole, right? Delta mixing U per mole will be Z multiplied by epsilon AB minus epsilon AA plus epsilon BB by 2 multiplied by XA XB plus RT XA ln XA plus XB ln XB. So this is the final expression for the quasi-chemical model. And regular solution model just takes all of this and gives it a name omega. There we go. Now we catch our breath.
Can you tell me what quasi-chemical means?
Quasi-chemical means that we actually thought about this enthalpy of mixing from a bond-based perspective, right? So in thermodynamics, we skip it, right? We really don't talk about bonds or even atoms, right? We just say mole of everything, we don't care. But this is the first time that I'm actually looking at a bond strength, right? So it's just a name for that one, the quasi-chemical model. This is our quasi-chemical, and it's also known as Bragg. Is it Bragg or Braggs? You seem to know Bragg. Is it Bragg or Bragg? Braggs.
Bragg.
Bragg. Okay, we will trust you. We'll trust Matt. Bragg-Williams approximation. It's easy to generalize it. We won't be doing it here. Instead of just thinking of pairs, you start thinking about triples of atoms and things like that, and you can come up with a whole hierarchy.
So
Okay.
we can actually like account for the behavior A and B with like epsilon AB.
Exactly. Exactly. That's why I like it a lot, because you can measure epsilon AB, right? And the thing about epsilon AB, it's the bond strength between carbon and hydrogen, right? That does not depend on the environment or anything, right? The potential energy curve is defined for carbon, hydrogen, right? You can do an accurate experiment and measure these things. And yeah, so it's a really, really powerful expression. Hopefully you can see why it's so powerful, because it tells you how do two things mix together in terms of the individual bond strength. So it's really, really beautiful. Any questions about this?
Show the epsilon equals,
Hmm?
bond depth.
Yeah. Yeah, yeah. So here, just let me remind you that
And then that only worked because we assumed that there wasn't a lot of PV work.
yeah, you can think of it as PV work. It worked because we assume that PV stays constant. There is no change in volume. So what Steven said earlier is actually correct. We assume that if you assume that it's all happening in a constant volume at constant pressure, then it's easy. But PV exists, but for solid state systems or liquid systems or liquid solid systems, approximating the enthalpy with internal energy is not a terrible approximation. Okay, and this is something which will happen to you in your research careers. I think that you will be approximating energy with enthalpy. And it's okay if you don't have gases involved. If you have gases involved, then you have to be very, very careful. That's what we did over here. Okay. So now we are moving to, well, ethanol water mixing. That's what we are going to study. And we are going to construct an actual phase diagram. And this part I will do today, and I will repeat all of what I'm starting from now. Make sure that you don't let me skip this part. I will be like, that part was clear, right? And you'll all be like, clear. I hope one of you goes like, no, please repeat that again, okay? So I want to repeat this part because it's a long break after Thanksgiving. So after Thanksgiving, we'll talk more about phase diagrams. Actually, let me open this focus. After Thanksgiving, we are continuing. So we did quasi-chemical model today. We are going to talk about construction of simple phase diagram and the common tangent construction, which we'll probably see after Thanksgiving, the lever rule. And then I want to take a slight step back and talk about Legendre transforms and connect free energies with each other. You know, I skipped it deliberately because I wanted to give you these practical things that are useful, right? And then go back to Legendre transforms. And once we do Legendre transforms, we will come back to phase diagrams, talk about things known as miscibility gap and spiral decompositions, talk a little bit about equilibrium constant. It's a lot of topics, but it will be quick, you know, because you have the fundamentals clear, so all that stuff is not very hard. So we have 4 classes after Thanksgiving. We will be doing all 4. Okay, there will be a homework which will be released the first day after Thanksgiving. It won't be very long, it will be the final homework.
Wait, that's it. Only 4 classes after Thanksgiving.
Yeah. Woohoo! 2 weeks.
Oh, by the way, I checked like the week of the finals, I were doing the exam. On the first week,
Exam is on the day, exam is like an 8 a.m. exam. Sorry, it's the university set time. You can look it up.
yeah, but what I mean is which day, like Tuesday, Thursday.
Oh, you look up the UMD calendar, you will see it's a Saturday morning. It's explicitly written there. If your class happens Tuesday, 11 a.m., your exam happens this time. There is only one option. I will confirm it. Yep, it's terrible. It's really terrible.
13th of December, 8 a.m.
Yeah, it's the Saturday morning, 13 December, 8 a.m.
8?
Saturday?
No, it's not. It's not Saturday.
It's not Saturday?
Sorry,
We have an exam on 14th.
Oh, okay.
15th is also Wednesday.
That will make it even better. Yeah.
Can you break down?
Oh, I bring donuts every exam. Yeah, no problem. Yeah. Not gluten free. It'll be normal donuts. It'll be like, but then I hope you all eat it because last time I brought it and the students were like so distracted by the exam, no one ate it. And then I had to eat like 12 donuts.
Yeah, just say like final exam whole semester. Take the days from December or.
I will post it on Slack. You will see you can find it, the schedule. It's very clear. If your class happens Tuesday, Thursday, 11 a.m., your exam happens this time.
Oh, really?
Yeah,
No,
Sanjana will help you.
It's 13th.
30?
Is it Friday the 13th? No? And it will happen here. It'll be 2 hours. Yeah, okay, let's come back to this. You'll all be fine. Don't worry.
Finals week starts on the 13th.
It's the first day
Yeah.
of the finals week.
So it's the 3rd.
You'll be free soon. And I think I will grade it like that day. And I will do like a live slacking.
I
Like
don't believe you.
oh, this time I will. I want freedom. I want freedom this time. And I will be, you will be able to tell from like I will be like, oh, now I'm listening to Taylor Swift, which means it's all going smooth.
Why are you posting these sample solutions?
When am I posting sample solutions?
Yeah.
Oh, good question. I want all of you to go back and try the problem that why is the isothermal steeper than the adiabatic. I want you all to get it yourselves. A few more days, then I will post it. Because when I will post the solution, it will be like, oh, yeah. A goes to B, B goes to C, C goes to D, D goes to C. Now I understand it. No, please suffer a bit more. Okay, so we did the regular solution model. Let me write down the expression once again before we go to the free energies, and that's before we go to more phase diagrams. So our regular solution model, delta mixing G was omega XA XB plus RT XA ln XA plus XB ln XB. And we drew this for two cases, right? We drew it for omega less than 0. For omega less than 0, the omega XA XB term is a parabola, right? And it's negative always, right? So that one looks like this. And the entropy of mixing term, that always drops down with a slope of minus infinity. Remember, the integrand is not here, the L'Hospital rule. It's like this. So the sum of these two is going to be a very negative number, right? Irrespective of whatever temperature you have, right? So the sum of these two is going to be something that looks like this at low or high temperature. What does it mean? It means the two systems are perfectly miscible. So the two things that mix together are not, some people call it mixable, but I think miscible is also a word that I learned, so I keep using it. Mixable, whatever you want to call it, okay? At any temperature. For omega more than 0, we saw two cases, right? I want you all to think and tell me, when does omega positive look like the omega negative case, at low temperature or at high temperature, and why? Dosia, you want to give it a shot? So let's look at it carefully, okay? So in this expression of enthalpy of mixing plus entropy of mixing, temperature shows up only for the right part, right? Only for the entropy of mixing. So at high temperature, you expect only this term will dominate, right? So as you go to very high temperatures, the effect of omega becomes immaterial, right? Because if you have T is equal to infinity, it doesn't matter whether omega is positive or negative, right? So if omega is positive and you go to very high temperature, things mix, right? At high temperature, if all of you have like consumed 50 bottles of Red Bull and come to the class, you will all be just jumping around, right? It doesn't matter whether you like each other or not. You'll be jumping from one corner to another corner, right? So that's how you can think of temperature. So omega positive at very high temperature looks similar. What looks similar? Delta mixing G looks similar, right? The delta mixing H, the parabola, is now going to be positive, right? Because omega is positive. But it's a teeny weeny parabola. It just doesn't matter, right? The entropy of mixing contributes so much. Why is she laughing? Laughing at the teeny. So, but the problem happens with omega positive at low temperature. And that's when we get interesting behavior. And I drew that curve last time. It looks, I will just draw the delta mixing G. That tends to look like this. You get a little hump in the middle. You have a competition between energy and entropy, okay? And by the way, it's a sin to draw a graph without labeling the axes. So I just committed a sin. This is xb is equal to 0. This is xb is equal to 1. Okay, and this is delta mixing G. Because in this case, the enthalpy of mixing is positive. The entropy of mixing drops down, but it is negative, and the overall sum of two things. And we know why it drops down first. It has to drop down, right? Because when you go to the two ends, the exponential drop dominates. So it always has to drop down, but then it picks up, right? Because omega is high and you are at a low temperature, right? So you're seeing entropy, enthalpy competition. We are going to spend some time talking about this curve after Thanksgiving, this second case, right? This is very interesting because it leads to what is known as phase separation. You can, in the same system, you can have two phases forming with different densities. We will talk about this after Thanksgiving. Today, I want to talk about two systems that are perfectly miscible at any temperature, like ethanol water, and just try to understand what happens over there and actually construct a phase diagram. So what are we talking about? What are we trying to do here? We will work with omega less than 0 case to construct phase diagram of.
So meaning that we're working at low temp.
No, this applies at any temperature.
Oh.
Because remember, omega negative, the temperature just didn't matter. It mixes at all temperatures. Yet you think, well, why do you need a phase diagram? It should be very simple, right? Yet there is a phase diagram, which is super interesting.
That omega bigger than 0 at very high temperatures.
We are not talking about that yet. That we will do after Thanksgiving. So after Thanksgiving, I will resume from here, okay? And then we will go to that other case also. To construct phase diagram of a two-component fully miscible system with two phases. So we have ethanol and water, okay? We are changing the fraction of ethanol and the fraction of water, right? Together they have to be sum up to 1, right? Mole fractions have sum up to 1. And we are changing the temperature. What happens to ethanol when you heat it? Huh? It vaporizes, right? So we are interested in liquid vapor. These are the two phases that we are interested in, okay? Liquid and vapor. So what we want to do is to construct a phase diagram where one end is xa is equal to 1, xb is equal to 0. The other end is xa is equal to 0, xb is equal to 1. And this thing is temperature. And we saw such phase diagrams for water, right? But that was not a composition temperature phase diagram. That was a pressure temperature phase diagram. So we are going to construct such a phase diagram for ethanol and water. Does anyone remember how such a phase diagram looks like? In PChem labs, if you have ever done a PChem lab, you have used such a phase diagram. If you have ever done fractional distillation or things like that, you have used it. It's a lens. Remember? You're right. It looks like. It can be left sloping, it can be right sloping, it can be symmetric, I don't care, but it's a lens structure that appears. Now, through your superior knowledge of the Gibbs phase rule, you know which region should have how many phases. In this region, it's going to be liquid. You can do G is equal to C minus P plus 2 and see that it is consistent. In this region, it is going to be vapor. And in the middle, it's going to be liquid plus vapor, okay? So in your PChem lab, if you have ever done a PChem lab, you have played with this. You have actually used this. And later we are going to also study about Lever's rule, which tells us exact details about this phase diagram. So you might be like, you have only 4 classes left and you seem to be overconfident in how much you can cover. Now, trust me, I will cover everything because it's not a lot. I did it in the past also, so I know exactly how much time it takes. So it's going to be, of course, if you all ask me lots of questions, which is great, I would really appreciate that. But then you might think if I ask you a question, I will put you on the blackboard. But I don't think that's going to stop you all from asking questions. I have a feeling. We will cover everything. Worst case, we will do one extra class, but I don't think that's going to be the case. So we are going to construct such a phase diagram starting from free energy curves that look like this, okay? So ethanol water mix perfectly, right? It's not like oil and water. You can keep adding ethanol to water, it will mix. This, I cannot help but remember this story. When I was growing up in India, I was in a, it's not a small city, but it's The Indians here might know it. It's a city called Patna. It's not a small city, but it's kind of like not a very developed city. So every day at my home, we used to get milk from an actual cow. The milkman would bring the cow. Yeah, I mean, and I would feed like bananas to the cow, banana peel, because I would eat the banana. And then the cows love the banana peel. But every time the milkman would try to dupe us. So he would have a bucket, and the idea was that he would milk the cow, there would be milk in the bucket. But he would come up with water in the bucket, and he would start milking, and then it looks like milk. So we had an instrument which basically used something like this phase diagram to tell you the fraction of water in the milk he had. And my grandfather would come out with this equipment and put it in the bucket and try to measure. And that's how we would find. And then we would change the milkman, new cow. Anyway. So let's get back to this. How are we going to do this? So what is this telling us? This phase diagram, what does it tell us about very high temperature? Which phase do you expect to happen at very high temperature? Vapor, right? It will be kind of crazy if you still have liquid. If you still have some liquid forming, it's not high enough. Heat it even more. At very, very high temperature, it should all fully vaporize, right? So if I try to think about that at very high temperature, and this is the final curve I'm going to draw, then I will stop. At very high temperature, vapor should be the stable phase, right? So if I go to my free energy curves, so this is G, this is delta mixing G versus XB. XB is equal to 0, XB is equal to 1. We know that the big picture here is that you can draw such a curve like the black one for the liquid phase, and you can draw such a curve for the vapor phase. Okay, you can draw two different curves. And we are talking about the phase diagram, and all of, by the way, I should have been clear. This is at a fixed pressure, right? So at a fixed pressure and at a very high temperature, which phase should be the most stable phase? Which state function should we look at? Gibbs free energy, right? Because we are talking about pressure and temperature. And if at very high temperature, only vapor exists, what does it tell us about the free energy of vapor with relative to free energy of liquid? Vapor free energy should always be lower, right? So we are going to get two curves, one for the vapor that's going to look like this. And at any concentration, the curve for the liquid will also be always negative, but it will be higher than the vapor curve. Okay, so this is G liquid, and this is G. Oh no, I did it absolutely wrong. Terrible. This is G liquid, and this is G vapor, right? So at any concentration, G vapor is more stable than G liquid. What we are going to do next time is to study these curves. How do they move as you change the temperature? What's going to be our equation in order to find that? How do we study how does free energy change with respect to temperature at constant pressure and number? We use the fundamental equation for G, right? What is the fundamental equation for G? That is dG is equal to V dP minus S dt plus mu dN. So partial G by partial T at constant pressure by N number is minus S. So the game plan for next time will be to realize that the vapor has more entropy than liquid. So the vapor curve will move steeper, more sharper than the liquid curve, something like that. They will all go up actually, but the vapor will go very quickly and the liquid will go slowly. And again, next time I'm going to start from here, from this recap point. Okay, so see you after Thanksgiving. Enjoy your turkey or whatever you eat.
One question. So this is, I understand this process, delta G mixing was fixed, right?
Yeah.
So how can you comment on delta G of liquid is higher or delta G of vapor?
No, this is delta G mixing if you had a pure liquid phase.
So, but that means that So this is basically liquid A, liquid B, delta G of mixing
Yeah, yeah,
liquid.
yeah.
And then this is liquid, vapor
Vapor
A,
A, vapor B. Yeah, yeah,
How do you know that the vapor has a higher delta G of mixing with the liquid?
We're gonna have
Because here you can only say compare G liquid and G vapor, not the delta G mixing, right?
Wow.
Olivia, please.
Let me get back to this one.
Like-
I